at our Center for Connected Multimodal Mobility, just to introduce you to our center. Our Center for Connected Multimodal Mobility, which is a US DOT Tier 1 center. This is a unique center for our state, focusing on future transportation system. So we are doing unique work. So our work in cybersecurity is second to none. So we have developed several systems, software to protect the future transportation system, transportation cyber-physical systems. So I think that would be really contribute to the future system and make our journey much safer, secure. Our center is extremely active in security research. So we are coming up with technologies that can bring in new direction to security. For example, we are looking at using software-defined network in securing the transportation cyber-physical systems. Say a vehicle is attacked from outside, so their brake system, anti-lock brake system, and other braking system, parking braking system are attacked. So those will not work. We've developed a artificial intelligence-based system using the software-defined network technology, which can detect an attack in a vehicle and also mitigate the attack in real time.
Being able to collaborate with faculty from Clemson University, University of South Carolina, College of Charleston has been great for us because we get to combine our resources and do great things. So I feel it's vital. Being a part of the Center has played a key role to our success and for the benefit of our students.
The project has been very helpful, given that not each institution will have all the resources that they need to be able to accomplish the project goals. For example, for our case, we were able to send our student to Clemson to utilize their automated and connected vehicle system. Teamwork works great than we can imagine.
We are working with several other companies in the state that are very supportive of what we are doing, because we have so many industries situated in South Carolina. They are very interested in transportation, mobility. So I see that it's a perfect match. We have the expertise from our center, the faculty at Clemson, other universities in South Carolina. We have great talent that are already producing results, that are producing software on cybersecurity and automation, and we have all these transportation companies. So I think this is a perfect marriage to make our state a leader in transportation technology. So this is an overview for center. So this slide, I'm showing the transportation cyber-physical social systems. So the physical system, there could be pedestrians, electricity grid, vehicles, any users of the transportation system will be a part of the physical system. And then we have a cyber system. It could be cloud computing, it could be edge computing. So they make up the transportation cyber physical system. So what we did, we thought that a social system should be an integral part of CPS. So we are working towards TCPSS, which is Transportation Cyber Physical Social Systems. Why we added the social components as a part of our research? Because we need to serve everyone equally. So to make sure that we our research are promoting social equity, and also we are enabling the human-machine interface in a seamless fashion. And also all this will create an environment that will promote user acceptance. So and it had been a great experience for us by bringing the social component. So we are looking at different things, integrating different knowledge. So the fundamental insight, so we are looking at the society and human system, and then we are looking at security, privacy, and resilience. And another slice of the pie is the data and systems. So we are looking to fundamental insights in these areas. And then we are looking at what are the technologies that will enable them. So here are some examples. So we are looking at the software-defined networking. We are looking at artificial intelligence. We are looking at the policies, even cyber law that would impact our research, especially cyber security and resilience. So one unique thing about us is the technology integration. So I always say, show me the money. So whatever we are doing in research, we are validating in the real world testbed. So we have a IoT testbeds. So it's a compilation of many testbeds. So we call it a cluster of testbeds. Specifically, we call it Greenville Pickens area cluster testbed. And it houses a community of over 1 million. So they are a part of a testbed. So we have this transportation cyber physical social system testbed, and every research we are doing, we are validating in our testbed. So we have multiple testbeds, and I will touch on some of those in the future slides. So in the TCPSS, we have different groups. We have the end users, which are the people, different groups of people. We have the control, which is controlling the autonomous vehicle, the controller. It could be a controller controlling the traffic signals. And then we have the communication, which is communicating between the physical system and the cyber system. And we have sensors. We have a roadside sensor, roadway sensor. We have autonomous vehicle sensors, connected vehicle sensors. And then we have actuators. So once the controller, say in an autonomous vehicle, for example, decides it's time to press the brake, so the actuator will initiate that. It will either press the accelerator or press the brake and any other control system in the car. So all this have a security threat because there are so many attack surfaces. So they're vulnerable to external attacks. So we are looking at different risks. As you can see, some of the risks I listed underneath the end user control, communication, sense, and actuator. So we are looking at all the risks that are associated with attack surfaces on these components, and we are developing hardware and software to mitigate these risks. And you will see some of these risks are addressed in our projects. So I'll go through some example projects. This is very important. So this is our foundation that we are not only trying to secure the transportation cyber physical systems, we are trying to secure the IoT environment in a city, in a region. So the Internet of Things environment includes different cyber physical systems. For example, you have transportation CPS, electricity grid CPS, it could be a building CPS. So in a smart city, all these different CPS will communicate with each other in a horizontal fashion. So you can see that the sensor layer, they are communicating, different sensor layers are communicating horizontally. So is the communication layer and compute and control layer. So if we are protecting one CPS very, very diligently, but not another CPS in a smart city, then we'll be vulnerable. Because if one CPS is attacked, the attack can propagate to other CPS. So we're looking at security from the Internet of Things aspect so that the threat does not propagate to any other cyber physical system. So the entire city will be then at risk. We are looking at the vertical security. So in a cyber physical system, as you can see, the communication is vertical. So we're looking at that, how to secure within a CPS, how you secure the compute and control node, how you secure the communication system, how you secure the sensor layers. So we are looking at this within a CPS, how you can protect these components, but also we are looking at how the communication can propagate the threats from one CPS to another CPS. So at the end, so we have to secure the end user. So as you can see, the different diverse groups of end users will be impacted if your CPS or IoT are impacted. So our focus areas are in two areas. One is security and resilience of TCPSS and human-oriented autonomous decision-making. In security, we are looking at privacy, access control, and then we are looking at the cyber security and resilience. So, and you can see that all these are color-coded and we are showing in the bottom. And I will, if you have any question on any of this, please let me know. So now I'll show resilience. So the resilience, we have defense in depth, which is the identify cybersecurity and privacy risks using defense in depth strategies. Then secure by design, so which is the integration of security measures into the system development process. And resistance, ability to passively prevent or minimize harm from cyber attacks. And then recovery, so that would be the ability to actively recover from a harm. So if the attack has already taken place, how you can recover from that attack. So in our center, we are looking at security and resilience on the three sides. One is the infrastructure edge. So that is the physical system. It includes this, different physical, either it's a cloud node or the edge node. And then we are, so it's a fixed edge. So we can call it fixed edge, and then the communication that provides the connection between the physical world and the cyber world. And also we are looking at the sensors, the in-vehicle sensors. So those are mobile sensors. So we have to treat the security and resilience of mobile sensors in a little bit different way than the fixed edges. I will now talk about this research that we are doing in these three areas with some example projects. The first is about the infrastructure edge. So cloud computing is a part of our infrastructure. And as you can see in the diagram, so we are working with different clouds. So we are working, say, with the cloud that are owned by state or cloud computing or at Clemson University. And also we are looking at the public cloud, for example, Amazon, Google, IBM. So we're looking at all those different cloud system and how those can help transportation system. But at the same time, how to protect these public clouds or the private clouds. So we are doing extensive research on cloud security. And you can see that usually in a cloud infrastructure, you'll have a software as a service, platform as a service, infrastructure as a service. So these are the primary services. And then you have a message broker, which is distributes your data across different transportation users or transportation services. So now this is the function, but what is the problem? Cybersecurity problem. So in terms of the cloud, securing the CV data in the cloud is an issue. Scalability of the cloud security solutions and data privacy in the cloud. So these are three primary components we are looking into for security related to the cloud. And related to the communication network, we are making sure that the communication network is secure. So there is no one can hear what we are sending from one node to another node. You're working on the encryption. We are working on the quantum encryption, which is we are doing some work on that. We are looking at if any other types of attack that can disable the communication network and that can propagate to the communication network, such as denial of service. It can cripple the system, and the attack can happen on the communication network. On the mobile node side, say for example, for the connected vehicles, we have to look at the authentication of CVs, validating the CV location, and establishing trust between the infrastructure or the cloud computing infrastructure and with all the CVs. So that's an important task. Unless it's trustworthy, then the security will not occur. So how to build that trust is also our research focus. So our research focus in the cloud security specifically are in these areas: infrastructure as a code, integration of blockchain with AI, quantum optimization and quantum AI, 5G. We look at other communication options too. We are looking at so 4G. We have our own cellular towers in our field, in our smart cities. So we have LT towers. We are using CV2X. So we do a huge amount of research on communication. We also have developed system for heterogeneous wireless networking. So based on where you are or where the vehicles or people are and what are the requirements of the application. So the communication network will switch automatically based on the need and mainly seamlessly. And also we work on network function virtualization. So we can we can go from the proprietary hardware to in software environment. So we can virtualize in the functions in a virtual machine. So one project I would like to discuss here. So this is on protecting the in-vehicle sensors. So say we have this control area network. All the different components are connected in a vehicle system. So for example, the brake control unit, the engine control unit, and the energy control units, all are connected to the controller area network. So, and we use the real data. So from Kia Soul, we collected data on their canvas or control area network. And then we attack those data. So with the different types of attacks. So but those are based on false information. So here you can see in this diagram at the bottom. So once we have an attack, the red line, you can see that the frequency is shifting, and it can create a lot of problems when the vehicles are autonomously controlled or some functions of the vehicle are autonomously controlled. So now once this attacks happens, so the vehicle could be in trouble, and sometimes it is not visible. So if you have a false information attack in like a very quick attack, and the deviation that the frequency deviation you are seeing, it may not be visible by any detection system you have. So what we did, we tried the quantum model to detect that attack. So you can see here, we encoded that CAN features. The first row was the normal, and the second row was the attack data. So that's so we encoded the data of the CAN features. And after we ran our models and compared with our model being the quantum classical neural network, and we compared with just only quantum neural network, and then we compared with a deep learning model, LSTM, and then we found that our hybrid quantum classical neural network performs the best. As you can see, we have the highest accuracy, 94%. And so there's a lot of reasons why it happens, because the way we are encoding, and so the quantum is providing additional support in achieving higher accuracy for our quantum neural network model. There's another project we completed. It is on V2 infrastructure application. So we developed a software called CVGuard. So the CVGuard resides in a cloud, either it's a public cloud or a private cloud, and it is connected with the different roadside units. And the roadside units continuously sends data that it receives from vehicles to the cloud, and the cloud has an algorithm that is looking for the data coming from different RSUs. It is looking for any deviation from some policies it has stored in the CVGuard controller. So it is a policy-based attack detection. So it has different criteria that the data should conform to. So for example, the speed should be in this threshold. The location of these vehicles should not go beyond this threshold. So there are a lot of policies embedded in the controller. And when the CVGuard controller sees any abnormality, it sends some small functions. We call those microboxes to the roadside units that is being attacked. And that microbox actually implements different strategies, countermeasures. So, for example, one countermeasure could be if it detects, you see in the circle, there is one attack vehicle, and it identifies that is the attack vehicle. Then the CV guard controller can inform the RSU through these microboxes that cut any communication from that attack vehicle, and it will do so in a millisecond. Or it can also take other actions too. For example, it can cut that attack vehicle from a particular channel and just keep it the data coming in one particular channel while knowing that that is the attack vehicle, and then can take action by following that vehicle's future activities. So now let's see some examples of security and resilience of the communication network. So we are working with software-defined network. So in this example, so there was a heterogeneous wireless networking option. So we have multiple layered security in the communication. So here I'm just showing with two. So say here we have a signal vehicle coordination. So say, for example, with the ATMS now software, you are communicating with the signal. Signal is sending you the signal phasing and timing information or the SPAD data. And the vehicle is sending the basic safety messages such as location, speed, the angle, steering angle. So now they're communicating this data, the vehicles and the signal controllers, and that actually enables a lot of applications and that can promote operational efficiency, safety. Also, it will help to reduce pollution if we enable these applications through vehicle to signal coordination. But if the network is attacked, the network that is enabling the communication, in this example, say it was a communication was through a particular medium, right? So, and then, so what we did, it was initially with a DSRC, and DSRC network was attacked. So, and then once we found that DSRC network is attacked, and we sensed it because we have a roadside device, it is running an algorithm to detect for such attack. When the attack is detected, it with the software-defined network strategy, it is instantly switching to to Wi-Fi network. So we can have different options: Wi-Fi, LTE, CV2X. So once it senses something is attacked, we can use the software-defined network to switch to another network instantaneously. We demonstrated our system, this network switching system, under cyber attack at the Las Vegas Consumers Electronics Show. So as you can see, the demo framework, so if you can compare with the left side, so there is an attacker. They are attacking the Wi-Fi access point, and the Wi-Fi access point is sending then. So it was supporting communication to different vehicles. The red dash line, and then we have a algorithm running. So if you look at the right figure, so we have the NVIDIA Jetson TX2 computing device. It was running an intelligent algorithm to detect any attack on the network. So when the NVIDIA device detected, it's just representing a computer, any attack in the network. So what it will do, it will instantaneously switch from, it was in the Wi-Fi, it will switch to LTE. So this is how it was going on. So the NVIDIA TX2 was detecting the attack, and then once detected, it was sending to the SDN controller that, so this network is attacked, and within a millisecond, the SDN controller will instruct the SDN switch to switch from Wi-Fi to LTE. So it was very appreciated by the audience. We showed it in real time, how fast it was, and that how effective it was in preventing attack on a particular application. Because once we notice there is an attack, we'll immediately switch to a different network. So here is an example of attack on the network. So there was an application running. It was on intersection collision avoidance. So we had a major road, no stop sign, minor road on the, as you can see on the left, with a stop sign. And so sometimes it's a problem because the minor road traffic may not have enough sight distance. So although there's a stop sign, the vehicle may start crossing from the minor street, but there might be a major sight distance problem. And so when it starts crossing the road, a vehicle on the major road it did not see could crash with it. So there could be accidents. So what we did in our research, we actually attacked the roadside unit, which was running the application, the intersection collision avoidance application. We attacked that roadside device with denial of service attack, which means that we flooded that device with unnecessary data. It is a very common type of attack. And then see what happens. But then we had our software that we developed, the CVGuard, so which is in a cloud, and it is monitoring this particular roadside unit. And when it sees that there is an attack, it will just immediately stop that attack. So it will take that attack vehicle out from the network. So once we implemented the CVGuard controller, our software, we saw a significant improvement in safety. And we are representing safety in terms of conflicts. As you can see, percentage of conflicts on the graph, on the right side, the top graph, percentage of conflicts before our software implemented in the cloud, which was monitoring the roadside infrastructure, roadside unit. So it was higher, but once we implemented our software, the conflict came down. And on the bottom diagram, you'll see that on the x-axis, the minor road versus major road vehicle ratio. As the vehicle ratio is increasing, which means that you have more minor road traffic, so the conflicts is going up. However, for attack CVGuard, without CVGuard, but one good thing you can see that we are significantly reducing conflicts because we have the CVGuard protection. So we saw that the intersection safety was improved by 60% with CVGuard when the roadside unit, and consequently the application, intersection collision avoidance application, was attacked by cyber attack. So now we talked about the cloud security, we talked about the network security. I will now give an example of security and resilience of in-vehicle sensor with a project. So this is one of our favorite types of research. We look at adversarial attacks, all kinds of adversarial attacks. So our team members, my students always are looking for ways to improve resilience against adversarial attacks. So as you can see in the attack, so a stop sign may seem as like a 45 miles per hour speed limit sign. A 25 miles per hour speed limit sign in a residential neighborhood could be seen by the autonomous vehicle perception module as a 65 miles per hour speed limit sign. And these perception modules are in autonomous vehicles. So autonomous vehicle controller will think that this is like it's not a stop sign, it's a 45 miles per hour speed limit sign. And then the actuator, as I was mentioning, the actuator will then, rather than stopping the vehicle by actuating the brake, it will just put on the accelerator, it will actuate the accelerator, so the vehicle will move forward. And in an intersection, that could result in major crashes, even fatalities. And so the example I will give you is with the LISA traffic data set. So it had criteria, the type of data it has. I'm just showing on the left. And you can see on the right side, right picture. So when the actual traffic sign was like this, how it was misclassified. So this slide is just for examples. That 45 was shown as stop. This is sometimes it could be shown as a different sign. So the attacks could be targeted. So the attacker may try to make a stop sign look like a 55 miles per hour speed limit sign, or untargeted. So, but in the untargeted attack, it just creates a perturbation without any intention of making it any type of special sign. So just make a random perturbation, and it can, so the perception module will perceive as a different sign, but it's on target, so it can be anything. So this is the impact of adversarial attacks. So an attack vehicle is creating perturbation in the AI module, which is used in the perception module in autonomous vehicle to recognize signs, recognize objects. So you can see that we have different types of signs and the success rate. So you can see that CW attack, when the adversarial attack was made with the perturbation in the AI model, so the success rate for attack was 100%. So the curved left sign would be seen as something else all the time. And these are some example attacks, FG, SM, and BIM attack. But we are using all available attacks on the AI models to test our resilience algorithms. So this is an example of the mitigation measures on adversarial attack. So you heard about that if you use a different layered protection, defense in depth, then if one system fails, the other system can be successful in providing protection against cyber attack. So here we are using 3 different methods at the same time. And if so one system fails, the other system will be able to protect. So here we are using random filtering. So we are randomly cropping a particular sign and resizing to transform the input image. So it is not recognizing the sign as a whole. You're just cropping different parts of a sign. And then we are using ensemble learning. So we are using different classifier model so to classify particular sign. So the autonomous vehicle, we have an ensemble of learning methods. So if one classifier model fails, the other classifier model might be right. So say it will be very hard for an attacker to deceive all different classifier models. And then we have a voting process. So whichever, say there are 3 different classifier model running. So if the most vote is for from the models is that this is a stop sign, then it will select the sign as a stop sign. So we have a voting process, plurality voting. And then we are using the local feature mapping. So we are also training it based on the different text words in a sign. So then it can, if it fails to, the other 2 methods fails, so random filtering, ensemble learning, then the local feature mapping will be able to recognize the sign correctly. So we are running all 3 these methods at the same time. And we are not showing any result in this one, but we found that this is significantly improving the protection against adversarial attack. So I will show. So that was a method that we had a different protection strategies running at the same time. This is another project where we ensured that our resilience against adversarial attacks are enhanced. So we use hybrid quantum classical model. As you can see on the left, so there's a stop sign and there's a noise. So the square box, a noise. And then we actually did this. We used the ResNet 18 for feature extraction. So that is in the classical processing unit. And then we have the quantum processing unit. So we have 3 layers: data encoding, variational quantum circuits, and measurement. So that's a part of quantum processing unit. And I'll show that in the next slide. And then we have post measurement. So what the post measurement layer tells us what sign it is. So in the example case, in this flowchart, it will tell us that whether it's a stop sign or it's not a stop sign, it's something else. So in this project, we created and evaluated 140 quantum circuits and selected the quantum circuit that provided the highest attack detection accuracy. Attack resilience accuracy. And then you can see in the flowchart, we have the data encoding, and then we have the variational quantum circuit, and then it is generating the different the performance for each circuit. And then the one that we see the performing the best, and we are using that to determine what is the accuracy. We use that variational circuit in our resilience model, so recognize different sign, so how it improves. So we are using the classical model to recognize the sign, and then we are using our quantum classical model to recognize the sign, and we are comparing which one is providing us the best result. As you can see here on the left portion of the bar chart, with a perturbation coefficient of 0.05, we have a higher accuracy for hybrid classical model, sign classification accuracy under adversarial attacks. So the AI model in the autonomous vehicle was attacked, and with a coefficient of 0.05, so we have a higher accuracy for hybrid hybrid quantum classical model compared to just a classical model. And also it is performing better when there is no attack in terms of recognizing the sign. So the perception model recognizing the sign. When the perturbation coefficient increased, which is significant, 1 from 0.5, so we saw that because there's much more noise, so the gradient sign attack was not performing overall for either hybrid or classical, but still our hybrid model was better. So we are also looking at security and safety in terms of autonomous vehicles decision making. By nature, autonomous vehicle is supposed to be defensive, but we want to make the autonomous vehicle more situation aware. So when it senses that it needs to act a bit more aggressively, it can do so. So it can have a, depending on the situation, it can react differently at different times and at different location. So this is a video that really happened. So the front vehicle was a human-driven vehicle, and the picture was taken by the autonomous vehicle, which was following this human-driven vehicle. The human-driven vehicle knew that the vehicle behind is an autonomous vehicle, so it was just suddenly stopping, so making a risky situation for the autonomous vehicle. So these type of things could happen, and we all know about road rage and aggressive driving. And if the human-driven drivers see an autonomous vehicle driving defensively, then there could be some unpleasant situation. So we try to address this situational awareness. So this is the example that we looked at a vehicle. So the left turning vehicle, the orange vehicle is our autonomous vehicle, and on the major road, and the white vehicle is the human-driven vehicle. The driver is acting aggressively. So when the autonomous vehicle is turning to turn left, then it senses that the vehicle behind it is aggressive. So we use different criteria to determine the aggressiveness of the vehicle behind the autonomous vehicle. And once we noticed that the aggressiveness is actually going beyond certain threshold, then autonomous vehicle is going in a different mode of operation. So it is becoming a little bit more aggressive in terms of how soon it tries to turn. But at the same time, it has to turn left very safely. So you can see that at that time, autonomous vehicle is taking a little bit more risk, but not the risk level that could create accident. And so it perceives the vehicles around it and tries to determine the aggressiveness. But what we found in this research that although the autonomous vehicle was not acting defensively as it does in other situations, our traffic measures were fine. So you can see on the right side of the graph, that average travel time for our situation-aware connected autonomous vehicle, the travel time was improved. So we had a 58% savings in travel time when the opposite traffic, so the opposite traffic where is the white series of 4 vehicles coming, there's opposing vehicles. So when 658% reduction in travel time with 800 is 52, but when it, so significant amount of traffic on the opposing lane, 1,000 vehicles per hour per lane. So we reduced the travel time by 62%. So these are our enablers. So we have a state-of-the-art lab in our Floor Daniel Engineering Innovation Building. So where we have developed scaled autonomous vehicle. We have a lot of software and hardware. We work with the software-defined network switches and other control devices, controllers for autonomous vehicles. And also we have different software. So you can see that we use pre-scan, we-bot, those are robotic simulators. So we can simulate autonomous vehicles. We actually teach a class. I teach a class where the students will use pre-scan. And then we have traffic simulator. You have the open source Sumo, but we have access to all simulators. And then we have network simulator, NS3, Mininet. We have adaptive signal control software that we use in our connected and autonomous vehicle research. We have a signal vehicle coordination. So most of the signals in our smart cities are connected. So if you have a connected vehicle, it can talk to the signal. And we're expanding our smart city testbed. And as I mentioned, we do a lot of work with quantum computing. So we use the quantum computers owned by IBM. We have a great collaboration with IBM on cloud research and quantum computing research. So we use their computers. We have the Xanadu and Pennylen, and AWS has a bracket where we can access their quantum computers for our research. So we have a one corridor, we call it South Carolina Connected Vehicle Testbed. It's like several miles of roads. We have our own communication network, and we have connected vehicles moving. We have connected signals, and also we have an extensive computing system. So and they are layered in edges. So we have the roadside edge, and then we have the middle edge, and we have the system edge. So all these different edges collaborate with each other to support the different CAV operations in terms of mobility, in terms of energy, sustainability, and in terms of safety. So we have also so in addition to this corridor, smart corridor, so our whole Clemson city is a transportation cyber physical social system testbed. We have signals connected, we have our communication infrastructure, we have our own intersection safety system. For example, we have the pedestrian safety system that uses a video-based system to detect pedestrians, especially they generate pedestrian safety messages, and it can pinpoint the location of each pedestrian extremely accurately. And then once it senses the vehicles around the intersection and pedestrians, and then it develops a risk profile that whether there's any risk of accident between the pedestrian and the vehicles. And if the system observes or detects a risk, it will notify the pedestrian through cell phone and the vehicles through their in-vehicle app. So we have established a quantum AI lab. We house the main lab at Benedict College. So, and we are doing a lot of research in that, the state-of-the-art research. Actually, I'm offering a course this semester, graduate course on quantum computing, quantum optimization, and AI. It's a collaboration between our center and the physics department at Clemson. So we are, I think, leading some of the research in a very innovative area. So my students presented recently 2 papers at TRB on quantum AI. So we also have several autonomous vehicles, and our autonomous vehicles are open, so they are research ready. So this one vehicle that I'm showing here, the open CAV, so it is mainly for research. So and we can collect a lot of data, and so if you look at the back of this vehicle, just many computers collecting data continuously, and while we are doing research on security and different operations. Also, we have the SCTAC, a closed testbed. So we can. So we are doing autonomous truck platooning project. So we cannot do that in the real world first. So we are testing it in this SCTAC testing facility. And then we have the famous Clemson University International Center for Automotive Research. I'm a faculty at this center as well. And so we have multiple labs on connected and autonomous vehicles and the state-of-the-art facility. So we do extensive research through CU ICAR. And last year we got this big center from the US Army. So we are developing unmanned autonomous vehicles for unstructured environment for the US Army. So we are doing very interesting projects on autonomous vehicles for unstructured environment through this new center, and the Viper GS. So this is a new Army center. So this is also a capability of us. So we have doing continuously field tests. So we just don't use simulation and develop model. We test in the field. So that's our the uniqueness. Everything we do, we validate in the field. And so we are working with this agency or organization, International Alliance for Mobility Testing and Standardization. So we are in the process of identifying the different test beds that can be used to test and certify autonomous vehicles. So the head of this organization is a great collaborator of us. So Dr. Joachim Teiber, so we are doing some interesting thing with him. And we are actually organizing a conference on this testing and certification in Florida. So it will be March 8, 7, 8, 9. So I'm a global conference chair for the conference. So our focus will be on testing and certification of connected and autonomous vehicle. So this is the conference that we'll have from March 7 to 9. Yeah, so it will be in Florida, near Orlando. So because of our unique work, so we received the Ieee Award. This is it's a very prestigious award. So if you look at the website, before Google received the autonomous team received it, and Berkeley's PATH program. So we are very proud to receive this year's award, IEEE Institutional Lead Award. So they said in the citation, contribution to the cyber physical transportation systems by addressing sensing, communication, and computing aspects of computerized mobility. So you can see that we are very comprehensive. So we are just not looking at sensor or only communication or only compute. So we are looking at all three aspects of CPS plus social side of it simultaneously. So I think that's why we are successful in what we do, because we are looking at the cyber system, physical system, communication, and social system all at the same time. So our research is addressing all four aspects of TCPSS. And so our DOT is a supporter of our work. So we are very happy with what we are doing. So you can visit our website to find out more about us. So on our security and resilience research. So this is my talk today, and please, I'm open for questions.
Thank you so much. It was very interesting and very different domains you did touch today. So any question?
Yes, this is Kareem Horn. I have a question. So in your SDN, when you detect an attack and it's able to switch
Yes.
networks, do you have any protocols, or what's your process for if like the attack is coming from one of the vehicles? Because if you
Yes.
switch the network, the vehicle will reconnect to that network and continue the attack.
Yes. So we determine first where the attack is coming from. So we have an algorithm running so that detects that where the attack is coming from. So what node the attack is generating from, and we have a protocol that how we switch in real time to one network to another network. Yeah.
Is that card disconnected from the network, or how do you handle that node?
Right. Yeah, that's a very good question. So we can, so we know that it is communicating through this channel in this radio. So we disconnect. That's one option. But also we have other options too. We can open a special channel for that. So we'll switch. So it will not send data with all vehicles are sending data. We'll open up a special channel. So we want to just monitor. We just play with the attacker. So where so we just want to see that where they are and what they are doing. So we can notify the law enforcement authority to go after that attack vehicle. So we kept open different options, but yeah.
All right, thank you.
So any other question?
Yes, please.
So while others are getting ready to ask more questions, can we go please to the slide that you were discussing about the situational aware control of autonomous vehicles?
Right.
I think that was a turning left scenario. Yeah. So you mentioned that the autonomous car here is taking some risk, but not that much. But anyway,
Yes.
to reduce the to avoid encountering with the aggressive driver that is coming through. So I have a bunch of questions here. First of all, and as an autonomous car, perhaps with having some passengers in the car, how we as a designer and
Yes.
designer of the controller and so on, how much ethically we are allowed to take some risk on behalf of the passengers, kind of things, right? So that's one thing that I was thinking. The second question that I had here, should we say a little bit more? Maybe that's what you mean to do. Say, you compromise the comfort. You are not increasing the risk. You compromise the comfort. You are not increasing the risk. And then to reduce the chance of encountering with the aggressive driver that is coming. Is it a more accurate statement here?
Yes. So we are trying to just in one word or two words, road rage. So we want to avoid this road rage, which are happening. So if you look at different news that autonomous vehicles are a target of road rage. So yeah. So exactly what you said. Yeah, Ali. Yeah, exactly.
Yeah. Okay, I see.
And
But coming back to my first question, even though you may not have here increased the risk, as a sort of designer of the autonomous controller, there are some risky situation, and then for which there has to be some risk taken. Just wanted to know your thought on that. How should we approach I mean, there is a risk that is coming, a dangerous, an aggressive driver is coming, and then there might be some risk that that the car has to taken. So how should we think in that way?
So as long I'm okay if that if the autonomous vehicle takes some risk, as long as they are not taking a risk that they will have an accident with the oncoming vehicle. So we looked at the conflict. So we were avoiding the conflict definitely. But you are right that so if they were more defensive, it would have less risk. But they are taking a little bit more risk. But not so much that there is a high probability of conflict. So, but they are taking some risk. Yeah.
Right.
So, and one so that so this paper is published in the IEEE top journal, IEEE IoT journal. So this is like a very high impact, over 10. So if you want to know the detail of that, so this is published in the IEEE IoT journal. So I have Dr. Saqib Khan. So it was actually his research. So you want to so do you have any opinion about that or?
Yes. Yeah, thank you. I was listening to the discussion and I also agree. So what we did is that we looked at there was an optimization function that we wanted to make sure that the comfort level of the passenger is ensured while the autonomous vehicle is trying to clear the intersection. So you see like there are different gaps that are shown on the slide, the blue color gaps. So if the autonomous car is very defensive, so it will pick the highest gap where it will be more comfortable to pass. But when we say that it's taking a risk, we are just saying doing that. It's selecting a narrower gap to make the left turn.
Yeah.
But still, it's making sure
Safe.
that it's safe. The passenger comfort is ensured, and it's not impacting the approaching vehicle's speed.
Right.
Yeah.
But I think that it will be, the risk will a little bit go up, but still it is manageable. You are not taking an unnecessary risk.
Right. And then on the opposite line, the other cars are autonomous or constant speed in your simulation, or no, they were having random speed or whatever.
They were all human-driven cars. They were just having their different. We were following some speed distribution, so the network was calibrated. They were coming at their own speed.
I see. Okay. Okay. Interesting. Thank you.
Thank you.
Let me ask you a question. First of all, it was really a great presentation, very detailed. Thank you. My question is, since your detection algorithms are online,
Yes.
so you are assuming that you have bank of attacks.
You have, could you repeat the last?
You have bank of attacks, meaning that you have a repository for known attacks.
Right. Very, yeah, I know where you're going. Yeah, so we have addressed that. Yes, yeah.
But then the question is, what if there is an attack that you are not aware of it?
Right, that's an excellent question. So we work with adaptive security. So we may not know. So we work with some models that we don't know about the attack. So it can very quickly learn that this is an attack and then have adaptive security. So that is a major problem. So, yeah, so what I showed you is with known attacks, but we are also doing some projects with a change point model. So if there's unknown attacks come in, so how you know that is an attack and how you provide countermeasures to it. So yeah, so we are looking into that, but that's a major problem. I will not say that we solve the problem, but we are looking into that extensively. But that is actually the major problem, because the attack that you're seeing today, it will not be the attack of tomorrow. So the adaptive security, so how you can in real time come up with a solution and detect them as attack is the research question of tomorrow. So that's a major problem. Yeah.
This is for my own curiosity. Your center name is Cyber Physical Social Systems.
Right.
Can I, okay, there is a reason why you picked this.
Right.
But the two areas that you mentioned as part of the two major research trusts that you are
right.
covering, but it's not addressing the social part
right.
of the cyber physical system.
Right. So yeah, right. Yeah. Now the project I showed, it was not showing the social part to it. So, but this project, I'll say that it is taking into consideration what is going on in the society. So I'll say that this probably out of the three projects, this is related to somewhat the social aspect. But but we are doing projects that social aspects are integral part of it. So I talked just briefly in the introduction that we have clusters of testbed, the Greenville-Pickens County, Greenville-Pickens cluster of testbed. So here we are involving so the population, especially the smart city that we have in Clemson. So we are organizing the users of the system either it's we are working with autonomous vehicles or electric vehicles. So we are involving the users. So and then we are getting their feedback in real time, and then we can change the system based on their feedback. But the projects I showed, the two projects earlier, I did not show. Those were not related to the social aspects of things. But our test beds that we are doing everything, so the society is an integral part of it. And also another thing, but it's a very good point. So I'm just showing, we have like how many, like we have probably 50 or 60 projects, right? How many projects we have done? So I'm just showing 3 projects, the snapshot 3 projects. So, but there is like one project we are working on. We are done with the Benedict College. We are looking at autonomous vehicle and how they are like how they are not conforming to the social side of things. So we are looking at the equity of autonomous vehicles. So we have some projects that are focusing on the social issue of CPS, and we are saying that. So, for example, this is an interesting topic, and our group has worked on this a lot. So for the CPS, right? So the cyber physical system will require that your city has a good public infrastructure, right? So what I showed in the test bed, you will have extensive communication network. You have this layered computing, the edge computing, the middle layer computing, the server layer computing, the cloud computing. But so in every city, in every area, you have to have that in order to make the connected autonomous vehicle CPS happen, right? But do you think like in a rural area where they are trying to fix the roads, the potholes, they will be able to have this CPS system for connected and autonomous vehicle? So we are saying that we are by this CAV CPS, which we think would be everyone think would be the best option, but we will not be ready with the CPS infrastructure. Maybe some areas which they have a lot of money to invest, they can. But while we are struggling with the infrastructure investment, so it might not be possible. So we are extensively looking at the social side of CPS. Yeah.
Okay. I shared with you a link.
Yes.
One of our trusts as part of this secure and safe assured autonomy.
Yes, yes.
Is we have technical challenge area 2 that basically addressing issues related to security breach.
Right. Okay. Okay.
But now this is for urban air, basically for air vehicles. But I thought that this may be.
We're taking a picture, so we'll look at it. Thank you.
Yeah.
Thank you so much.
And then, as part of this social system that you have, then are you looking at topics like rumors?
So are you saying rural areas?
No, rumors. Rumor.
Okay, all right. Rumor, no, we have not looked into that. So yes.
Like Facebook, like in the Facebook, we have rumors that.
Yeah. No, we are not looking at that. So I don't know, Dr. Vareva Harris at Benedict College. She's vice president. So she's involved on the social side of it. And then we have this the civil rights Miss Pam Foster. So they're looking at this social thing, and we are looking at from the historic side. We are looking at what happened, like in the country for the last 200 years in transportation, the equity, and we are framing our research on the social side onto that. So they are helping us a lot on the social side of it. But no, we are not looking at rumors. So that could be something interesting to look at. Yeah.
Right. Thank you.
But yeah, so we have some social scientists we are working with. And I mentioned just 2 of them. So they are very involved with our project, the equity and autonomous vehicle.
Thank you.
Okay, so one thing I showed you that in the near future, the testing and certification will be very important for CAVs. But what we are saying that it should not just be the testing of the vehicles, it should be the testing of the CPS, so or CPSS. So it should be when you test, the test should be done on the vehicle side, on the compute side, and the communication side at the same time. So the alliance I'm working with, so you're looking at this all these three aspects plus social side. So we'll see that whether the things that we have, whether it satisfies the equity issues and any other social goals we have. So actually, I'm involved with this the development of this process. So I'm working with this alliance very closely.
Right. Thank you.
Yeah, but you made very good points. Yeah, so, but yeah, we are trying. So because this is our focus, we are trying our with the social scientists, the human factor scientists. We are looking into that, and I showed you the pie three circles. So one is looking at the human and social system.
Thank you so much. We are almost 4:09. Let's have if one more last question, and then I'll wrap up today's meeting. If there is any other question, we might have room for one more question.
Hello.
Yes, yes.
I have a question, and in your project you show that you're focusing on the planning attacks. So what types of attacks actually you are focusing more?
So is this like all types of attacks that we know of? So yeah, so I published a paper in the National Academy of Engineering. I can share Saqib can share the link with Ali. So on all the different kinds of attacks that can happen on CAVs. So yeah, so it was published in the NAE Bridge magazine. So we are looking at all sorts of attacks, but now one is the attack just on the sensing, compute, and the communication. So it could be false information. It could be like a phishing attack. And I have listed the attacks in one of the slides, and I show the risk. So there are different nodes, and the different kinds of attack can happen on different nodes. So in one of the slides, I showed all the types of attacks can happen. So on the sensing, so for GPS, for example, so I have an active project. It's going very well. The attack on GNSS, so the location services. So if your GNSS is attacked, so say with like false information, so and it is very easy to do that attack, and so your GPS will show that you are in Clemson, but actually you are in Greensboro. So and it could create a lot of problems if you can go in a wrong way. So we are looking at the GNSS attack. We are looking at the GPS jamming. So yeah, so and we had false information, denial of service. So all sorts of attacks that can happen on these nodes. And also in terms of the attack on the AI module, the perception module on autonomous car, we are looking at different types of adversarial attacks. So I showed some of the examples, the CNW, so like a list of attacks, and then what are the attacks that we are working? Can you just talk about it? What's the
fast gradient sign attack, Carnegie-Wagner attack, basic iterative attack, projective gradient descent.
Yes, but I understand this attack, but my question is most of the attacks, there's two kinds of attack, like black box attack and white box.
Right, we are doing both, black box and white box, both. Yeah.
Okay, but I think in your project, the projected gradient attack and other attacks are like, my understanding, those attacks are white box attack.
Yeah, but so we have projects, we are doing the black box and white box. So the adversarial that we are doing with right now with the 3 method that running same time, that was a black box attack, right? Yeah.
Okay, thank you.
But we are very comprehensive, and so there was a great comment about trustworthy. So we have an NSF ERC. So we are going to so ERC planning grant. So we are looking at trustworthy transport. So how you can secure and make the system resilient, so it will be trustworthy. So it cannot be trusted, right? So you cannot say that that people have to trust it. It's not valid. So what we are saying, as you mentioned, one of the audience members, that yeah, we are trying to make it trustworthy. So yeah. Yeah, so we are looking at the black box and white box also attacks both.
Okay.
And yeah.
Thank you so much. I think it was very nice. I mean, a lot of these terminologies and whatever maybe we have been doing with basic and security and whatever or control communication, but bringing this to the context of transportation. So showing that both you had the deep knowledge both on the transportation side and then on the other side of it, and bringing these two together in a well integrated way. That was really inspiring.
Yeah,
Thank you so much for
I
today's
teach
talk.
class. I teach a class on security and resilience of CPSS. So,
Right.
yeah.
Thank you. Yep. Thank you so much.